ado, it is my pleasure to introduce our first speaker, Stefanie Guenther. Stefanie got her PhD in RWTH Aachen University in Germany. Hope I said that right. She is now a postdoc at Lawrence Livermore National Laboratory. And today she will talk about a scalable multigrid approach for layer parallel deep learning. Take it away, Stefanie.
Yes, thank you, Sami. So yeah, I will present work that I've been doing during my previous postdoc in Germany, in Kaiserslautern, with my boss Nicolas Gauger, and there was a very fruitful collaboration with Lars Rudotto from Emory University, Jacob Schröder from University of New Mexico, and Eric Suhr, who will also be presenting in an hour. Since it's very cool, I want to start out with a quote that I found. It's a quote of the NVIDIA CEO talking at a conference in 2019, and he says that modern data science is the fastest growing field of computer science today, and because of several factors, it has become the fourth pillar of the scientific method. So he talks about 4 pillars, so that typically we would consider 3 pillars of the scientific methods being experiments, theory, and also more recently computing. Now, lifting AI to that same level, so a pillar of the scientific method saying that this is the way the way how we discover previously unknown laws. So lifting AI to that same level has created a little bit of a discussion amongst the scientific community. On the one hand, because of the many challenges that are still to be faced in machine learning, but on the other hand also because it's not entirely clear if AI by itself can reveal previously undiscovered laws. And while this is certainly true, it's also the other argument that actually AI and machine learning is already changing the way we do research in scientific computing. And there's this whole new field of scientific machine learning evolving, where machine learning really helps us do the work we want to do better. And I have 2 examples for it, which are both here at the National Lab in Livermore. But there's many more. There's a whole bibliography that you can find here. It's a little bit not so much up to date, but still very interesting. So these 2 examples, one is from the local National Ignition Facility at the lab, where they use machine learning trained on simulation and experimental data from inertial confinement fusion. And they want to build or they trained the machine learning model to build a surrogate to identify a surrogate for those simulations to identify robust implosions. So robust implosions are the ones with the highest energy yields, and they have a 9-dimensional parameter space, so 9 knobs they can tune for their experiments. And now using machine learning, they can really identify the ones with the best energy yields. So this is very cool. Another example is machine learning to a couple different solvers. This is also at the lab. They wanted to investigate the dynamics of a certain protein, which is thought to be involved in the development of cancer. And they have a macro scale solver for it and a microscale solver on the molecular dynamics level. And in order to couple those together, they trained a machine learning basically in the middle in order to identify regions of most importance from or most significance from the macroscale solver, and then in order to decide where to start a microscale simulation. So using machine learning, they are now really able to cover the full range of the large and the small scale behavior of that protein. So this is all really interesting and cool, but as I said, there's many challenges still involved with that. And I grouped them here together in basically 3 categories. One is more conceptual, so a question of interpretability, robustness, are questions like what can we learn from the trained model? Robustness, what happens if we change few parameters in the trained network? Does it give us reliable results? Domain awareness is an interesting topic, how to include physical knowledge. And then numerical challenges, which go hand in hand with computational challenges. I guess. So we have huge dimensionalities, a lot of parameters. Network design is difficult, a lot of hyperparameter tuning and trial and error. So this goes really hand in hand with computational challenges, which I think get more, or also very significant when you think of scientific computing, where data sets or available data easily scales in the order of terabytes, and runtimes, training runtimes can be in the orders of hours and weeks or even more. And so in this talk, I want to look into basically two techniques that what we learned from optimal control in HPC and how we can mitigate some of the challenges, especially considering runtime and memory requirements for the training of neural networks. And so to start, this is an outline. I want to first start making again the connection of deep learning with optimal control. I guess most of you know that already, so I'll go quite quickly there. Now we'll talk about two approaches. One is introducing a greater concurrency, so more parallelism across the layers of a neural network. And the second one is a simultaneous training approach, which is a new way of solving the optimization problem in the full space. And yeah, you will see this is based on inexact gradient approach. So this is very quick recap to make the notation clear. So we want to learn a function for sure which maps x to y, and the model for our function is a neural network, which we feed on the left side with some x, some inputs at the layer 0, and then each layer of the neural network applies, for example, this formula. We have a nonlinear activation function, a linear term with a weights matrix W, and a bias term. And at the output of the network, we want to match, the output to the given data. And in order to achieve that, basically train or optimize for the network parameters, which I will denote by xi. So xi in bold. That means bold always means that we collect all the different layers from 0 to n-1 all into one big vector. So we optimize on xi, I have to minimize the discrepancy between the output, the predicted output and the true output, subject to the forward propagation of the neural network. Okay, so so the connection to ODEs comes in when you look at a particular residual, particular network, a ResNet, which looks like this. It has this extra term here, which is an identity for xn. And they came up with this residual type neural networks. They come in different flavors, but they came up with that in like 2015, where they won an image recognition challenge, a yearly challenge. And using this kind of network really helped being able to train deeper and deeper networks. So the networks before were more in the order of 5 to, say, I think this was 16 layers. And then we have this huge jump using just this tiny identity. They were able to go deeper and deeper, and trend goes further. So there's even networks with thousands of layers. I find this very intuitive, adding this identity here, because when I think of the easiest function that we would want to learn in machine learning, that would be the identity function. So learning the identity function when you have this term here is easy, because you just set all the weights and the biases to 0, and then you learn the identity function immediately. If you don't have this term, then learning the identity mapping from this nonlinear application of sigma and the affine term is kind of difficult. You would need to adjust all of those in order to get an identity back. So this is really, for ResNets, we start at the identity function and then learn from there. And here the connection to optimal control, then you can see it from here. So we can add a little delta t, which is like a small number. And then you see immediately that this is the explicit Euler of explicit Euler discretization of a dynamical system, which can look like this. So we now consider x to be a time-dependent function. So x is the state of the network being time-dependent. And in a discretized level, each time point is basically one layer. And now we just place the layers infinitely close together with this delta t. And then in the limit, we get this continuous ODE where the right-hand side is this activation function and a time-dependent weights matrix and a time-dependent bias. And then we have, for sure, deep learning can be cast as an optimal control problem for a final time objective function f, which is the loss at the final time t. And the constraints are now a standard ODE with the right-hand side, with some what you would call a design or control, a network state, and the time derivative of the network state. And at the zeroth time, we feed it with data. So having this continuous interpretation in mind, at some point, for sure, you would need to go back and discretize that again. So if you choose your explicit Euler scheme to discretize this, then you're back at ResNet, but you can also consider other discretization schemes, and we might hear more about this later in this session. To solve then the discretized problems, it's iteratively with the gradient methods. We start by a forward propagation, which is just a solve of this ODE for your data to compute the objective function. Then a back propagation step, which is the adjoint ODE solve, which propagates gradients backwards in time to get the gradient of f, and then use the gradient of f to do a network update in this outer iteration loop. And so in this talk, or the next part of this talk, we'll talk about how to speed up the first and the second step by introducing layer parallelism for the forward and the backward paths. So let me start with some common parallelization strategies. And here I want to thank Eric for these nice pictures. I couldn't come up with better ones. So common strategies will be either data parallelism or model parallelism. In data parallelism, basically replicate your network onto different processors and then split your data or data batch that you want to propagate through onto those different processors, and then do that forward propagation and the backward propagation in parallel for this distributed data. And then usually at the output and after the gradient computation, you would need to do some kind of an MPI or reduce some collection of the gradient. For model parallelism, that can go in addition to data parallelism. Here, each of the networks is distributed amongst the processors in this horizontal direction. So this basically is parallel linear algebra. So when you do matrix reflective products, you do this all in parallel for distributed states. For both of those approaches, we still have the serial bottleneck of the forward and backward propagation. So each of these black arrows here means that really the next layer, the following layer, has to wait until the previous layer has done some computation before it can start here. And people have come up with layer parallelism in the sense that they pipeline things through this network. So pipeline different input data and then go forward. But the problem of the serial bottleneck is still there in the sense that if you double the number of layers, then you would still need double as much time to go forward and backward, because it's still a serial algorithm. And this is what we wanted to change. So instead of having a serial forward propagation, we now introduce this parallelism across the layers, splitting different layers to different processors. And in order to break this just forward serial propagation, we add a multigrid scheme, or we apply a multigrid scheme to the forward propagation, where we update on coarser level. So we kind of skip a few of the layers and then introduce a coarser network across the layers that updates the boundaries between processors. I will talk more about this, just a few notes. So this is orthogonal to data and model parallelism. So we can do all of them and multiply, speed up should multiply. And the idea is basically coming out from parallel and time integration methods for ODEs and PDEs, where the most famous method is probably parareal. I have an example for for two-level, so for the forward propagation, a two-level multigrid example here to make the method more clear. Here, all the time steps are basically layers. We have the input layer here and the output layer there. And a multigrid, so we want to apply a multigrid scheme to the layer propagation. So we build a coarser grid by skipping few of the layers. And a nonlinear multigrid cycle usually consists of 3 steps. The first one is a relaxation on the fine grid here. Relaxation typically means get some approximation on the fine grid to your solution. And this is supposed to reduce high frequency error components. And then in the second step, you go to a coarser grid and solve a residual equation on the coarser grid, which reduces low frequency error components, but much cheaper because the low frequencies on the coarser grid are actually higher frequencies on the coarse grid. So this can be done fast because it's a coarse grid. And then we use the error approximation to update the fine grid approximations. So it's always these 3 steps. I want to go into a bit more detail how that actually works. So the first relaxation step, this is the first layer parallel step, where each processor starts from some initial condition at the time interval boundaries and just propagates whatever he has here, these interfaces forward through the interface, through the time domain that this processor owns, or through the layer that this processor owns. So this gives an approximation on the fine grid of the network state. And then so after this step, you will get a residual, which is non-zero right here between, right here at the boundaries of 2 time intervals. So the forward propagation of this guy would not correspond to what this guy has here. So this is a non-zero residual. And we solve this residual equation then on the coarser grid. So this is the second step. This is a sequential step. Here it's basically the same as on the fine grid. We have a forward propagation of the states. However, we kind of choose a very big time step. Same forward propagation with a big time step, and we have an additional correction term, which is the residual that we've just computed from the fine grid. This provides an approximation of the error at these interfaces, and this error then can be used in the last step, in the correction step. So we use this error to update the initial conditions at the time domain interfaces. This again is a layer parallel step, so this can be done fully in parallel for each of the time domains. Yeah, so as I said, the second step, solving the residual equation, is the only kind of sequential part of this algorithm. So we want to make sure that the sequential part is small. And in order to achieve that, we can apply the same method recursively to, well, yeah, solve the residual equation again with a multigrid scheme. And then we end up with full multi-level grid hierarchy, which you can cycle through with standard multigrid methods like V cycles or F cycles. And then you do this whole step 1, 2, 3 repeatedly until you converge to a solution that you want to. And I think I should mention, when you consider this picture again, so after the first iteration, since this guy gets the input data, after the first iteration, this whole domain will be the exact same forward propagation as we have in serial. After the second iteration, since we have the information here, this guy will be fully resolved, and so forth. So in at latest n iterations, where n is the number of domains that we have, this will give the exact same result as a serial forward propagation. Luckily, this whole process converges much faster than n iterations, so we don't need to wait for the forward propagation. But as I said, so this converges faster, and we still recover that at convergence, we still recover the same results as we had previously. The only difference is now we can do it actually in parallel because it's a multigrid scheme. I will write this a little bit differently in terms of a fixed point solver. So when you imagine this bold X to be a collection of the vectors from the first layer to the last layer all of the network states in one vector, then we can consider this multigrid iterations as an iterative scheme to update these the entire state over the entire network. Here I'll denote with H1 multigrid iteration, so one multigrid cycle going to the coarse grid and the fine grid again for some current approximation to the network parameters. And we can do the same, basically the same algorithm also for the backpropagation. Backpropagation equations, the adjoint equation are very similar. The only difference is that you have basically gradients, and it runs backwards in time. So we order this adjoint variable, which contains the derivatives with x bar, and we order them backwards from the last layer to the first layer. And then we can basically apply the same multigrid scheme as we do for the forward propagation. We apply the same multigrid also to solve the backward propagation process. One slight difference is that this takes as an input also the current approximation to the network state, because it's a nonlinear scheme. So we need, in order to get the derivatives, we need to feed it with the current evaluation point. Since this is a multigrid scheme, we actually do more work than a classical just forward propagation. It's more work. However, we can do this in parallel. So the speed up really comes through greater concurrency, and there will be a crossover point only if you have enough layers to parallelize over and enough cores to do the parallelization, then you will see some speed up. We can integrate that in a normal training, whatever training method you would have, you can still do the same training steps. It's basically just a replacement of the forward propagation by an iterative multigrid scheme and the back propagation, and then you get the same gradient up to some tolerance and use that in the update. And I want to show some results for scaling of this method. These are some like smaller size test cases that we wanted to get a feeling on how that actually works, what we can expect from it. And we have 3 test cases. One, what we call the peaks example, where the goal is to classify grid points in this 2-dimensional domain into 5 different classes, which correspond to level sets of a function. So these are the colors here. The second one is a bit more interesting. This is an image segmentation problem where the data consists of hyperspectral images, and the goal is to classify each pixel in those images into 1 out of 16 classes belonging to different land covers. And then the third one is a classical MNIST, where you want to classify grayscale images into 1 out of 10 digits. So we wrote our own neural ODE network, used the forward Euler discretization. So this is basically a ResNet. We used a ReLU activation function, which we smoothed around 0 a little bit to get rid of the discontinuity or the kink. And then we used this package XBreak from the Lawrence Livermore lab for doing the parallel in time integration. So this is a nice open source and non-intrusive package that provides time parallelization given a certain time stepping algorithm. We did not use any data or model parallelism to run these cases, because we wanted to see what is really the benefit of parallelizing only in time, because data and model parallelism really goes in addition to that. And we look first at the multigrid convergence for the state and the adjoint state of the network. So this is for one full batch gradient computation. And we artificially increase the number of layers and look at the convergence of multigrid iterations. And we see that for basically all of the cases, I omitted the last test case because it's basically the same. No matter how big we do, how many time steps we need, we still converge in like 5 iterations, a relative drop of 10 to the minus 9. So convergence of the multigrid scheme itself is fast. More interesting are the scaling results. So we have a strong scaling plot here where we again, for the peaks and the Indian pines example, we fix the problem size and we increase the number of cores. So fixed problem size means for fixed numbers of layers, we just throw more and more cores to it and then measure the time. And we see here in the beginning, since we do more work, we are actually slower than the residual, than the serial part. The serial runtimes are denoted here by this horizontal lines. And really see, in the beginning we are slow, but at some point there will be a crossover point, which is here around 16 or more like 20 cores going. And for the biggest test case here, we start out being relatively fast and then scaling down. Nice, strong scaling property. I think I should hurry up a little actually. Weak scaling plots show actually the speed up over the layer serial propagation. So here in these plots, we at the same time increase the number of layers, but also increase the numbers of cores to solve this on. And the layer serial part has been added as a reference. So this is just the classical forward and backward propagation, no multigrid. And for these test cases, sure, if you double the number of layers, you would need double as much time to go through that path. However, if you apply the multigrid scheme, since we have this constant number of iteration counts, we actually get a flat line in the runtimes. So that means that the speed up double anytime you double the number of the layers. Okay, I will quickly go through a simultaneous training. Maybe skip this one slide here, but talk about this. So for simultaneous training, the idea is, since we have an iterative scheme to update our network state in the adjoint, maybe it's sufficient to not fully converge to a full solution in the multigrid schemes. So basically, in this simultaneous training, we allow for an error in the network state and in the network adjoint state, so that we get an approximation to the gradient that uses inexact states and adjoints. And then this approximation can be used still in the same optimization scheme, but we add some kind of a preconditioner here, which takes into account for the inexactness in the state and the adjoint state. It's a little bit of a discussion between reduced space optimization and PD constraint optimization when we talk about reduced space versus full space optimization. In a reduced space optimization, you kind of get rid of the constraints and optimize basically only on the network parameters or on the design parameters. Well, in each iteration, you fully solve for the state and for the adjoint. Whereas in full space optimization, all at once or one shot, you would basically simultaneously solve for this coupled, for the full space variables. So you update your state, you update the adjoints, and only update the XC in a coupled iteration. As I said, for the designs or for the network states, we would need some kind of a preconditioners. In theory, this preconditioners should take into account the non-zero residual of the network state, so that the network update really knows about the error that we have done during forward propagation. Numerically, we do use that, and we do some approximation of it using either BFGS updates or some scaled identities. And some results. Here we do 2 multigrid cycles per optimization iteration. So inexact states, because only 2 of the iterations are done. We see, so this plot is there to show you that basically we reach more or less the same results with the simultaneous training that we would also reach with the standard full space training, reduced space training. So we get the same training loss more or less in the same number of iterations and a very comparable validation accuracy for both of the test cases. However, in this simultaneous approach, each iteration here is much more cheap, because we only do a few multigrid cycles and we can do that in parallel. So when we plot that same data over the compute time, then we really see a great benefit from here. Yes, for these test cases that we were running, we get a speed up in this order 6 and 4 and 8, which is not super great when you consider the number of cores that you use. But on the other hand, if a speed up of 8 or even 4 means to reduce the runtime from 40 something hours to 10 hours, then that's still something that you might to consider if you have the resources available. Okay, so this brings me to the end of my talk. I've been starting out with making the connection again of ODE, of network training and optimal control. And this really enables a lot of knowledge transfer from optimal control to scientific machine learning. Then introduce the layer parallelization, where we use a multigrid scheme to replace the forward and the backward propagation. So this really gives us a new dimension for concurrency and scalable machine learning. It also has the benefit of the distributed storage of network weights and the states. And then in the last part, I talked about simultaneous training, where you basically use inexact states and adjoins to do the updates, where we basically, it's an early stopping of the multigrid iterations during training. So yes, thank you. If you have any questions, I think there were some in the chat, but I didn't read them. Thanks.
Oh, thank you very much for the talk, Stefanie. Since we only have time for maybe one quick question while let's see, Andreas can set up his share screen.
I'll stop sharing then.
Yeah. Any questions from the audience? Maybe one quick one.
I think Shanshao has raised his hand.
Yeah.
Oh, yeah.
Hi. Thanks for the nice talk. I have a question regarding the data. So here it seems to be that all the data is shared across all the different machines, and because usually when we think about training using stochastic gradient methods, right, we usually have to split the data somehow. But here, when you want to match different layers together, you need them to be operating on the same data, right? How is data distributed in this case?
So you can still do what you did before with data parallelism.
Mm-hmm.
And then inside that, so being inside one of those processor blocks for data parallelism, you split this, but still these ones need to share the data. At least, well, yes, the first and the last one would need to store the data, right? So you split up your network along the layers, then the first layer and the last layer would need to have data available, input and output. The in-betweens just need the transformed states of the network. But the data is really on the, it's kind of like at the boundary of the time domains.
Okay, so the data is actually split in this case in different machines, different cores, let's say.
Yes, so when you still do data parallelism, you split your data still like normally onto different machines. And then each of these groups, like consider data parallelism as processor groups now, each of them will in addition split the time domain, which is the layer domain. And for this, the first and the last one would need the initial and the last data, so the input and the output data.
Mm. Okay, thank you.
Okay. Yeah.